Hi, welcome back to our chapter about quadratics and simultaneous equations. And today we're going to be talking about an interesting part of mathematics called inequalities. And in particular, how we have quadratic inequalities and how we can find how to find the solution for these. So let's get started. Now, an inequality is a lot like an equation, but instead of an equal sign, the statement uses one of these four signs that you probably recognize: greater than, less than, greater than or equal to, less than or equal to show that one expression is not or may not be equal to another. So we know already that a quadratic is something where you have the highest exponent 2, and the general form of a quadratic is ax squared plus bx plus c. So those are the two keywords that we're going to be talking about: inequalities and quadratics. Our aim is that by the end, we feel like we can solve linear inequalities and we can find the solution for, or the set of solutions that will satisfy quadratic inequalities two ways: graphically and algebraically. As we go through this, first we're going to look at a review of inequality rules. If you've done this in Maths D, this might be review or from previous years. Hopefully there's enough explanation here, if this is new, that you can pick it up and understand what's going on. Then we'll look at solving inequalities graphically and algebraically for quadratics. I think you have a handout about inequalities. And it starts off by saying an inequality is a mathematical statement like an equation, but using these symbols. Fill in what you think the symbol means here. Or what would you say this statement means? Pause the video and then we'll check them together here. Okay, let's try it. So if you have something written like this, it means x is greater than a. Now, you have to be aware of English word order, which is sometimes a little bit different than where you put the two things when you're doing it in Bangla word order. Those of you who also can do comparisons in Bangla. X is less than a is what this next one would mean. X is less than or equal to a, or x is greater than or equal to a. So in English, it goes from left to right. That thing on the left is what gets affected, and you can see that the caret sign or the inequality sign, it's bigger on the part that's bigger and smaller on the part that's smaller. Inequalities can also be represented on number lines. For example, if you have something like this, which we would read as x is smaller than or less than or equal to 4, we can show it on a number line. Maybe you've done this previously. It would look something like this. We use the closed circle above the number 4 to show us that 4 is included in the values because it could be equal to it. And we use the arrow pointing left to show that all values less than 4, this way, less than 4, are included. So the closed dot, your handout has this thing to fill in. The closed dot includes the value at the boundary. You might want to draw this in as an example. If instead we turned and said, well, x is just less than 4, how do we represent that? We draw an open dot. The open circle above the number 4 shows us that 4 is not included in our values, but any other value up to 4 could be. 3.999 is fine. An arrow pointing left shows us that all the values less than 4 are still included. So an open dot excludes, does not include, excludes means that the value at the boundary. Now it's your turn. Take a look at these A, B, C, D and decide which one would you match them to in the number lines. Okay, maybe you can come up to the screen and show, pause the video until you've tried it. Okay, welcome back. Hopefully you connected them to these number lines. That's greater than 2, less than 2, and if it's equal to or greater than 2, or equal to or greater than less than 2, we have these options. Okay, imagine there's a student named Aisha, and she says, I'm thinking of a number that's greater than -3, but less than 2. What number could she be thinking of? Give some suggestions. Okay, you give some suggestions. We'll pause the video. Welcome back. She could have had any kind of numbers. Anything that's in between -3 but less than 2. It didn't say that they had to be integers, so any of these numbers could be examples. She said her number is greater than -3, so if you said something -3, that doesn't get included, but less than 2. So it doesn't include 2 either. So if we were going to write this as a single inequality, sometimes we use two inequality signs to state a range. And it can represent two restrictions on a particular number. For example, here's the two restrictions. It has to be greater than 3. So we have open circles because we're not including -3, greater than -3, I should have said. And open circle at 2, we're not including 2, but any value in between them is included. So a number line of that would look like this. Try another one. Lucas says, I have drawn this inequality. You tell me what it is. What inequality is Lucas representing? Okay. Pause the video and have a try. Hopefully you come up with -1 is less than x is less than or equal to 4. Now you don't have to use x. You could have used any variable here, y, z. But if you say it in words, values greater than -1, but less than or equal to 4 is what we have here. Okay, try a few more. Here are some where you have two restrictions. See if you can match these number lines to these letters. Okay, pause the video until you've tried to go and tried it. All right, hopefully you match them up to these on the number lines. Okay, you can check your work, check what you came up with. So an inequality is sometimes you have values that have satisfy two inequalities and you can write them together. Here's an example. Here's a student named Jacob who says, to go on the swing ride at Shapnapuri, it says you have to be at least 2 years old. Otherwise you're too little. And Aisha says, yeah, but it's a young child ride, so you have to be 5 years and younger, 5 years or under. So how would we write this as a single inequality? We could write it as x in the middle, that's the age, has to be greater than or equal to 2, less than or equal to 5. And we would write it all together like this. If we put it on a number line, it would look something like, okay, I have the one restriction, I have the second restriction, I can use that as just two closed dots and connect all the way in between. We can also represent inequalities that don't overlap. For example, if I said x has to be less than 0 or x is greater than 1, I'd have two lines going in opposite directions. So here I'm representing all the numbers which are less than 0 or greater than 1. And we can do that too sometimes. The only values not included are values in between 0 and 1. So usually when you have a split region like this, you write them as two statements, this or this, we don't combine them. All right, so look here at again, you have a set of 4 number lines and 4 questions, and you're going to see if you can match which ones go together, okay? Pause the video and try it. Welcome back. Hopefully you match them up like this. Check your work, check what you did together as a class. Okay, great. Sometimes when you have a value with multiple inequalities, you end up with 2 things in the end, and sometimes one inequality actually overrides the other one. Let's look at this example. So what values would satisfy 2 is less than or equal to x and 4 is less than x? If I had these 2 and I said we have to have them both, here's what they'd look like on a number line. So x has to be greater than or equal to 2 and x has to be greater than 4. Well, if it has to be both the arrows are going the same way this time. The regions only start to overlap when you get greater than 4. So really, you only need that one constraint to represent both of these inequalities if they both have to be true. Here's another one. You try it. If I have x is less than 5 and x is less than or equal to 3, what can I actually have if I have to have both of them? In order to satisfy both, I have to have something that's less than or equal to 3. So sometimes to satisfy multiple inequalities that have 2 constraints, you only end up with 1 at the end. All right, look at this number line, and which of the inequalities, A, B, or C, satisfies x is less than or equal to 4, x is greater than 1? Okay, pause the video and decide. Okay, how many picked B? You are right. It is that region. Okay, it could be represented together and look like this if you did it in one line. Okay, try this one. Which inequality shows all the values that satisfy both x is less than or equal to 4 and x is less than 1? You'd have to pick A, right? To have a region that satisfies both. Okay, one more example. This time the values have to satisfy this pair of constraints, plus they have to also satisfy x is greater than 3. Okay. So let's think of them on a number line. The first one, x has to be between 2, it could include 2, it has to be less than 6. But the second one, x has to be greater than 3. So if I have to satisfy all of these, where are the values I could have? I could only have between 3 and 6, and not including either of those values, right? Because it has to be greater than 3, so 3 is not included. If you were going to say what integer values would satisfy both inequalities, remember what integers are, hopefully, you could have 4 or 5. They would satisfy. All right, let's try another one. If I had 2 ranges of values and I want to know what satisfies both of these, take out hopefully you have your notebooks, but jot down a number line and see if you could plot and figure out what would satisfy both of these inequalities. Okay, take a few minutes and then start the video again. Okay, so if you put it on a number line, hopefully it helps you to see it easier. That the first range of values is here. The second range of values is 0 to 5. And so to satisfy both, It has to be greater than 0 or equal to 0, but less than 3. So I have this small range that satisfies both, and the way we would write that in an inequality would look like this. 0 is less than or equal to x is less than 3. We usually put the smaller number down on the left and the bigger number on the right. You've probably noticed that. And that's just because it helps us to think the way we do on a number line, left to right. What integer values would satisfy these sets of inequalities? You could have 0, you could have 1, or you could have 2. Any of those would work. All right, here again is another one for you to try. You pick which answer you would pick out of this, A, B, C, or D. Okay, pause the video till you've decided. How many have picked B? You are correct. Here's what it would look like if you have both regions and then you combine them together, and that would be your best answer. Okay, so hopefully number lines help you to imagine inequalities, that they represent a region. Now, if you have equations with inequalities, some rules are just the same as when you solve equations. So for inequalities or for equations with an equal sign. For example, if you're adding or you're subtracting a number from both sides of an inequality, the inequality sign doesn't change. It doesn't affect it. For example, if I have something like a plus 4 is greater than 9, if this was an equation with an equals, we know what a would be, right? We would subtract 4 from both sides and do this in our head even. We talk about it sometimes as we move the negative 4 to the other side. And then we'd say, well, a is greater than 5. And it would be perfectly correct. Adding or subtracting doesn't affect the inequality sign. Now, keep in mind, we know that a can't be 5 in this case. It's not a solution. It has to be bigger than 5. So any value greater than 5, if I check it, it should work. So let me try 6. If I have 6 plus 4 is greater than 9, yeah, 10 is greater than 9. Okay, so that works. Let's check another one. How about 5.2? Is that greater? Yeah, that's greater than 9. And any value that's 5 or less than 5 shouldn't work. You can also check something like that if you're getting the hang of this. So try something like 4. Does that work? Is 8 greater than 9? No, it's not. How about 0.5? Is that greater than 9? No, it's not. Okay? So adding or subtracting something to either side doesn't change the inequality sign. Also, if you're multiplying or dividing both sides of an inequality by a positive number, the inequality sign doesn't change either. It stays the same. Let's look at some examples. So really, you can use this with any of the 4 symbols. Let's try less than or equal to. So if I have something here like 5a is less than or equal to 15, to clear that, I know I have to divide or I have to multiply by 1/5, right? If I do that and that's a positive 1/5 on both sides, nothing changes. A then is less than or equal to 3. The solution includes 3 or any number less than 3. And again, you could check it if you want to. If I put 3 in, it works. It's equal. If I put something less than 3, like 2, I should get something less than 15, which I do. If I put something more than 3, I should get something that doesn't work, which it doesn't. So if you were going to solve this inequality, what would be the constraint on B? We can subtract 5 from both sides, and B is less than 7. If you put it on a number line, you draw it like this. Okay, you try this one. All right, hopefully you find that x is greater than or equal to 8.5. And if you drew it on a number line, it'd look something like this. When an inequality has multiple steps, like a multi-step equation, you can solve it in exactly the same way if it's adding or subtracting, or if it's positive multiplication or division. For example, 5x plus 7 is less than 42. First, we can do the adding and subtracting and get rid of that 7. Then we can divide, and we come up with x is less than 7. Works just like an equation would work. You could check some values again. If I have to have something less than 7, let's try 6. And we can see, oh yeah, that works. Okay. If I try something really less than 7, it still works. The left side is less than the right side. If I try 7, I should get the same thing, which then is not less than 42, right? So it doesn't matter also which side of the inequality the x is on, as long as we're careful. You can't just swing it around like you can with an equal sign without changing the direction that the inequality goes. Okay, so if you had the x here on the right hand side and you were solving for x and you were clearing it and you get down to the last stage and you have 19 over 3, or you could do that as a mixed fraction, is less than or equal to x. If I want to write that with the x first, I can. I can have the x on the left-hand side, but I have to swing that inequality around with it so that I write x is then greater than or equal to 19 over 3. Or if you want to write it as a mixed fraction, x is greater than or equal to 6 1/3. So you just have to be careful if you're swinging the equation around that you don't leave it as an incorrect statement. Okay, now you try to see if you can solve this multi-step inequality. All right, you try it and then pause the video and then you can get started again. All right, welcome back. Hopefully you've solved the inequality and you found that a is greater than or equal to -1. So if you are checking some values, then you could try something. Try -1. It says it can be equal to it, and there it is. 3 is equal to 3. If you try something less than, greater than -1, then you should find that it doesn't actually work. Wait, greater than or equal to -1. It does actually work. And 5 is greater than or equal to 3. Sorry, I got distracted there for a minute. If I try something less than, then that ends up being not a true statement. Okay, try this next one. Pause the video and then when you're ready, you can check your answers. Okay, let's check our work. You should get b is less than -2. Again, you can always check some values if you're not sure and see if your solution holds up. If it is true where you think it should be true, and if it's false where you think it should be false. Okay, so we said now some of the rules for solving equations are the same for inequalities, but you might be getting the idea already that as we keep saying some of them, not all of them are. And the one that is different is this one, that if you are multiplying or dividing both sides of an inequality by a negative number, you have to change the inequality sign. You have to flip it. We'll show you some examples of this. Why does this happen? Think about this inequality. It's a true statement. -3 is less than 6, right? We'd all agree. I'd rather have 6 than -3. Taka. If I multiply both sides by -1, I'm doing the same thing to both sides. That's normally what we can do with an equation. But for an inequality, if I multiply both sides by -1, I would get 3 is less than -6. Is that true? No, it's not, right? So this is no longer a true statement. It's no longer valid. What would we have to do to make it valid? We'd have to flip the sign around. So let's try 5 is greater than 3. Maybe it works if all the numbers are positive. If I multiply both sides by multiply or divide both sides by -1, what will I get? I'll get -5 is greater than -3. Is that true? No, hopefully not. Hopefully you don't think so, because this is no longer a true statement. It's worse to have -5 than to have -3. So that's less. So what happens, maybe you can visualize by looking at this number line. If I multiply by a negative, the triangle currently has a larger value than the square, right? The triangle is 5, the square is 3. But if I multiply by a negative, it flips it to the other side of the number line. And the symmetry of directed numbers around 0 means that when you multiply it by that negative, the positions flip, and the triangle actually has the smaller value now than the square. So what you have to do is flip the sign. Lucas is trying to find a solution to this inequality. So he has moved the 4, he's subtracted 4 from both sides, and that's fine, correct so far. Then he divides both sides by 2, also fine. He just did it with a positive 2, but now he has minus x is less than 3. So he wants to get rid of that negative. If he multiplies both sides by -1, the new rule that we just talked about, and the thing that makes it a true statement, is you have to flip it and say, now x has to be greater than -3 if minus x is less than 3. So x has to be greater than -3. When you multiply or divide by a negative, the inequality symbol will change. So what would be the final answer for him? It would be, this is a different one. That when you get down to the point where you have to divide by a negative, you flip the inequality sign. Now, if you want to write this left-hand side to right, x is less than or equal to 3 in this case. So now you decide out of A, B, C, or D, which of these is equivalent to minus x is less than 5. All right, hopefully you pick D. Yes. If I have minus x is less than 5, I could also think about this in adding and subtracting. If I would add a positive x to both sides, then I would move the x over to the other side. I wouldn't be dividing or multiplying by the negative. And then I could say, oh, then I could move the 5 over and be subtracting it. And I would see that x has to be greater than -5. Okay? So you can think about these negative multiplying and dividing things. Sometimes you can solve them by just adding or subtracting the term on the other side. And it's personal preference which you find more efficient. But just remember that if you multiply or divide by a negative, you have to flip the sign. So here you go. Here's somebody who's doing this inequality and has decided to do it by subtracting 5 from both sides. So you get -6 is less than or equal to -3x. So now they're going to divide by 3, still have negative on both sides. So I'm going to divide by -1 and flip the sign. So instead of being less than or equal to, it's going to be greater than or equal to. You could do the same thing by moving the negative term to the other side, adding it on the other side. So you could add 3x to both sides. So 3x -1, keep the term, the inequality the same. Then I could add 1 to both sides. 3x is less than or equal to 6. I end up getting, divide by 3, x is less than or equal to 2. It's the same answer. So if you really prefer to add or subtract and not worry about changing the sign, you can do that. But if you multiply or divide by a negative, just remember that you have to change the sign. Okay, if we can deal with something that's a negative unknown, then you can could have x's on both sides of the inequality symbol. You solve them in the same way. If you want to avoid negatives, where it's possible, you can move the 2 to the other side so that you're going to end up with positive x's, not negative x's. It's just a good practice to avoid making things harder for yourself. If you followed through and did this one, you'd end up getting x is greater than or equal to 4. If you wrote it left to right, it would look like this. You can again, if you have unknowns on both sides, you can still check by putting something back into the original. If I take something greater than or equal to 4, so 4 should work. Put 4 in, and look, it's equal. I could put something greater than 4 in, and I should get a true statement, which I do. Okay, here's one for you to try with x's on both sides. Pause the video until you've tried it. Okay, welcome back. Now compare your answers to what's on the screen. You should get x's less than 7/3. Or you might have written that as a mixed number, that's fine. Okay, try this one. Pause the video. Okay, welcome back. Check your work with what's on the screen. You should get x is less than 2. Make sure that your inequality symbol is the correct way around. All right, hopefully you have some time, so you can copy these down into your notebook and try them, and you can pause the video until you're ready to compare and check your work. All right, pause the video. Okay, welcome back. Here's the answers for the work that you were doing, so you can compare and check your work. I'll put them all up on the screen, and then if you need to, you can pause the video until you finish checking. All right, let's carry on. So when you're solving inequalities, generally you follow the same rules as solving equations. But remember that multiplying or dividing by a negative, you have to reverse the inequality sign. Sometimes when you're solving inequalities where the coefficient of the variable is negative, you could add or subtract that term to avoid multiplying or dividing by a negative if you prefer that. If you're trying to find a solution to an inequality that has the unknown thing in the middle and it has 2 constraints, the recommended process is to just separate that into 2 inequalities, solve them both, and then put them back together at the end. I find it helps it to stay more clear. So write down one inequality, everything on the left side of the inequality and on the right side of it. And that one, if I divide, that would be x less than minus 2. Then write down the inequality that includes everything that's on the left of the inequality and everything that's on the right of it with that inequality, and solve that one. That would be, okay, x is greater than minus 5 when I deal with the negative here. Now I could draw these 2 things on a number line if I needed a little extra help. X is less than negative 2, so that would go this way, and it's greater than negative 5. So here I can see the region that's the combination. I could graph that on a number line, or I can just write it down. And I put the smaller number first, then I put the x in the middle, then I put the larger number on the right if it is a continuous region. So here are 2 other inequalities. How would you combine these? Pause the video and pick which answer. Hopefully you picked B, okay? which is the correct answer. This is what it would look like if you visualized it on a number line. This is the region that we're talking about. How about this one? What about here where you have an expression, not just a term in the middle? Okay. Again, you break it up into two inequalities, but you have to include that whole expression when you write the two different ones. So which one is it? It would be option number B. Please ask if that doesn't make sense, okay? You're splitting it into two things that you can solve. It also helps if you have multiple different terms with different coefficients. So if I had something like this, we can separate it into two inequalities and we can solve separately. You'd split it up into the first inequality and then you repeat that middle one because it has to be dealt with in relationship to the second inequality. And then you solve them both. And once you're down to your two things that x has to be following, then you can combine those solutions. If it is a continuous region, x is between 3 and 16, then you write it this way. If it's a split region, then you write it as two separate statements. You can pick a value to check. What's something in between? I could pick 5. That's something in between. And I check it all out and I do the calculations and I should get a true statement, which I do. Okay, let's look at another example of these. I don't know if you've done many of them, but you could try this one. So we separate these into two inequalities, and then we go ahead and solve them, and we end up with x is less than or equal to 5, and x is greater than 3. So if we combine these, we can see that they have a region between 3 and 5. Okay, here's another one for you to try. Pause the video until you've tried it. Okay, welcome back. Now compare with your answers here. You should get the region. 2 is less than or equal to x is less than or equal to 9. Okay, here's another one for you to try. Pause the video until you've tried it. Okay, welcome back. You should end up getting the region 4 is less than or equal to x is less than or equal to 5. Great, if you did it. Not all inequalities will have a valid solution that's true for always going to be true. So Laura, imagine there's a student named Laura and she says, well, I actually made up this inequality for me to solve, but I don't think it works. And why does she not think it works? If you separate it into two different inequalities and you solve them, you end up getting, well, x is greater than or equal to minus 2, and x is less than or equal to minus 5. And what's the problem with that? You don't actually have anything that x can be if it there's no values that satisfy both. If you were looking and saying, okay, it could be this or this, that's fine. But if you're trying to satisfy both, there's actually no solutions because it's a gap. There's no solutions where both are true. So if you have more complicated linear inequalities, you can separate them into two things and solve it more easily. If it is valid for both, you can write it as one single inequality, but not all inequalities will have a shared region. Let's talk about now quadratics, because that's what our chapter is about. And how do quadratics and inequalities relate to each other? You may have needed to continue on and have done this in a separate lesson, but this is the part from solving quadratics graphically. We're going to talk about that first, and then we're going to talk about algebraically. We know how to solve quadratic equations. We've talked about different ways to do that. By factorizing, completing the square, using the formula. We know that sometimes with a quadratic, when we solve it, we get two different answers. This particular quadratic equation has two solutions. It's a difference of squares. But if I said that instead of an equal sign, it was an inequality, what would that look like? The key word here, as far as graphically, is look. If we can graph something, we can look at it. We can get an idea of what does it look like. I've graphed x squared minus 4 is less than, well, I've graphed is x squared minus 4 is equal to y in this graph. So if I said x squared minus 4 is less than 0, where is that 0 line? When is the graph here below 0? We can see where y is equal to 0, it's below that. So we can define this as a region. And it's a region that's defined by what the values of x can give, or what the values of x have to be to get this region. X has to be between minus 2, and it could be anything up to positive 2, to be below 0. So when we graph this, we can see that it's a region. We could graph it and we could block out this whole region and say this is that whole section. So the solution to this inequality is this inequality with two constraints. X has to be greater than minus 2 or less than 2. If it was equal, it would be equal to 0. But below 0 is this part. Here's another graph. If I have this graph, x squared minus 1 is equal to y. Now, can you solve this inequality? If I say x squared minus 1 is less than 0, which answer would you pick? Okay, did you pick? Hopefully you picked B. You can see that the region minus 1 up to 1, there is where the graph is less than 0, where the line dips down below the line y equals 0. If you have a graph, something graphed, sometimes you can solve a variety of different inequalities with it. For example, if we go back to x squared minus 4 equals y, then you could solve all of these inequalities. So where is it less than 0? That means where is the curve below the x-axis, right? So that is here, which is between minus 2 and positive 2. Okay, so we've defined that region this way. What about where is this curve below 5? So we need to look at the line for y equals 5. Okay, where is the curve below that line? Well, here it is, this whole region. And if I was going to define that, I can see these points, and I check what are those x values? Well, x has to be between minus 3 and positive 3. And I can see that that whole region then, the curve is below 5. I could also say, well, x squared minus 4 has to be less than minus 4. Where is that region? You look at the line, y is minus 4. Now you have a problem, right? Actually, you don't have any line that's below minus 4. So you don't have any solution. The minimum point of the curve is minus 4. So you have nothing that is less than minus 4. Okay, now let's try some more. Here I've graphed x squared plus 2 is equal to y. Can you solve the inequality x squared plus 2 is less than 6? Pause the video and pick a choice. Okay, welcome back. I hope you picked C. That's the solution. That's where the line y equals 6 would interact with this curve. Okay, same graph, but what if I say less than or greater than 1? What would be your answer here? Pause the video, pick an answer. Answer here would be no solution. The minimum point of the curve is 2, so there would be no solution to this inequality. There is no place where x squared plus 2 is less than or equal to 1. Sometimes you'll see complex looking examples where you have a whole quadratic looking like the general form of a quadratic, but it's no more complex than the examples we've already done if it's already graphed. Okay? Here I'm looking at comparing this graph of minus x squared plus x plus 6 is equal to y is graphed for us. So I just need to look at the line 4 and see where is this curve greater than 4. And that's in this region, and that region can be defined by the inequality 4. Sorry, I pushed the slide forward too quickly, but between minus 1 all the way up to 2. All right, if you were going to do this same curve, but looking at where is it greater than minus 6, it would be in this region. X has to be between minus 3, it has to be less than 4. Sometimes the solution can be a little bit more complex. If I say, okay, x squared minus 4 is greater than 0, it's not less than. I'm not looking at that continuous part in between. I'm actually looking at a split solution. It could be either of these branches where it's greater than 0. So you can see that you then have a split solution set. X could be less than minus 2, or X could be greater than 2. Okay? It can't be both, but it could be either. So we might see a solution like this. If you've done any set notation yet in Maths D, in set notation they might write this as the union, X could be the union of where X is less than minus 2, or the set of all X where X is greater than 2. If you haven't done set notation yet, don't worry about it. This is just showing you what it could look like in set notation. Here's another graph. X squared minus 1 is greater than 0 is the inequality we're trying to solve. Okay, where is this greater than 0? Pause the video and have a go. You could have picked, hopefully you'd see that it's this region where it's greater than 0, where that curved line is greater than 0. You could have picked C or D if you know set notation. They're the same answer. All right, if you have something where you have a double quadratic inequality and you have graphed the thing in the middle, x squared minus 4 is equal to y, you could also define a region. Where is our curve greater than 0 but less than 5? It would be between these two black lines. So where is the curve in this place? It's in these two regions. If you shaded them in, it's in these two regions where it's between 0 and 5 for the y value. And so the x value there would have to be between minus 3 up to minus 2, or it could be between positive 2 up to positive 3. So that helps. Again, you could write that down in set notation. And you would have, well, it's the union of these two places. Here again, you have another one to try. you have a go and try it. See if you can solve where this region would be. Okay, did you try it? So we're looking at when is the curve greater than -3, but less than 0. So it's in this little section, these two parts of the line, which are defined by the x values that are shaded in here. And those x values can be represented by inequalities. Or you can write them in set notation. All right, here's another one to try. Now, you have this task A and B given to you on a paper, hopefully a handout given to you. So you can work on this in your paper. And when you've done this work, then you can carry on and correct your work by seeing what's here on the screen, okay? So you have question 1 and question 2 in task A, and then you can look at the video and check your work, okay? So pause the video for now, hopefully pass out task A to everyone, and yeah, now we're ready to check. Hopefully you've done it, and let's check our work. Okay, for A you should get -3. Yeah, I'm not going to read them all, I'll just put them on the screen, and you can compare your work to the solutions. Okay, and when you're ready, you can go on to question number 2 and check your work based on what's on the screen here. You didn't have to write it in set notation, but if you wanted to, you could for a challenge. All right, once you've corrected that work, we'll save task B for a bit later. When you're graphing things, you might say, hey, I don't want to graph everything. So how can I solve this? Or how can I figure out the roots of the curve? Can they help me if I can solve it that way? And the answer is yes. So if I have x squared minus 4, I know that the roots of that curve are +2 or -2 because I know how to factorize it. And that can help me to solve these. I can imagine the curve and I think, okay, well, where is this curve below 0? Well, it's between those two roots. And where is this curve above 0? Well, it's outside of these roots. And so I can define those roots. They help me to give the answer. Wouldn't have to graph it, right? You can check your solutions by putting in an sample. So if something was between -2 and 2, you could try it with 0 and see, does it work? Well, yeah, it does. -4 is less than 0. Or you could try it by putting something in that is outside of this. If I put -4, is that going to end up with greater than 0? Yeah, it works. Okay. So if you see something that is a perfect, this difference of squares, just knowing what the roots are helps you to solve the inequality, because I know that the roots would be at -12 and 12. So I can look for the solution to this inequality by considering the roots. When you put those roots in, you could check them again, and you could find out that, oh yeah, okay, I've done the right way. If I check my solutions, I can always correct them and see if I put something in that should work, does it work? We may not always be given a graph, but solving graphically might still help us. If we put something in that is, if we look at something and we're giving an inequality and we realize, oh, I could rearrange that to be a difference of squares, then I could sketch it and I could realize, oh, I can solve that really quickly by factorizing it. I know that the roots of that would be -3 and 3. Therefore, I could find the region and I could solve and find where that graph will lie. I could check it again by taking a value that's within that region and seeing if I come up with a true answer to know that I've gotten the right part of the region. So here's a couple for you to try. If it was said to you, rearrange this into the form of difference of squares and try to graph it to solve, what would you end up with? If I move the 4 over, I could end up with x squared minus 16, right? Well, what are the roots of that one? Positive and negative 4. So if I'm looking for where that curve is less than 0, I want the region between minus 4 up to positive 4. And I can check it, and I can see that, yeah, it works. If you have one where the x squared is negative, usually that would make a frowning curve, right? If I rearrange it, I could say, oh, okay, here's my frowning curve, and I want where the frowning curve is less than 0. So that's going to still, the roots are going to be 3 and minus 3, but I want the outside of this region. Okay, and so I can define that as a split solution set, where x is less than minus 3 or where x is greater than 3. You could have also, and you can check your work, but you could have also moved the inequality so that the x squared was positive. And if I did that, then I would say I'm looking for where this curve is greater than 0. But my curve would also be in the positive direction. And my roots would still be minus 3 and 3. And actually, you end up with the same solution set, but the visualization of it might look different. Okay, if you are given roots that are like a rearrangement of this inequality, which one of these could you solve with it? Okay, this is a bit of a challenge question. Which one, if I have 37 minus x squared is less than 12, which one of these inequalities can I solve if I rearrange this? Which one is it equivalent to? Okay, hopefully you can see it's equivalent to A. And the graph of it would be related to that, the root of 25, so it would be positive and negative 5. Now, if I could solve this one, and I can see where I'm looking where it's less than 0, this negative 1, actually I could also use that same rearrangement, could also be rearranged to be the positive 1, and it ends up being the same solution, the same region. So you could have picked A, you could have picked D in this case. So if you have something that is a perfect square, difference of squares, now you have the back side of your handout. This is task B. You can try these two questions, and then when you've tried them, pause the video, try number 1 and number 2, and then you can compare your work to what's on the screen, okay? Pause the video, try task B, back side of the page, and here are the answers when you're ready, okay? Hopefully you've tried them already now, task B, and here you can compare your work. You can look and see the region that should have been defined on the graph, and also some checking. Okay, number 2, if you're going to rearrange that one, what can make a sketch of it? There you have a perfect square, 64, so that relates to negative and positive 8. And how about this one? That one ends up relating to 100, and you can actually take it in the negative frowning curve, or you could have moved the things to the right-hand side and it would be a positive, but it's the same region that you end up defining either way. The region between -10 and +10. Okay, hopefully doing task B has helped you to feel like you can solve quadratic inequalities graphically. You have more of these in your textbook to try in the next section. So, and you can also recognize that x squared minus 9 is less than 0, x squared minus 9 is greater than 0. If you're not quite sure if you've gotten the right solution, you can always check to confirm. A sketch of a graph can really help. All right, we want to move on to solving quadratic inequalities algebraically. So we know now how to visualize algebraic inequalities graphically, and we'll go on to try how to solve them without a graph. So when we were solving quadratic equations, we did this in various ways. We could break it down and factorize them and see the roots that way, right? And these, we would get the two values of x could be -5 or x could be 1 in this situation that's on the screen. So how does this differ when we have an inequality? How do we do this algebraically? The main thing to keep in mind is that this is asking when is the curve equal to 0, but the inequality is asking when is the curve below 0? When is this whole line below the 0, y equals 0 mark? So even if you're doing it algebraically, visualizing or having a graph can be incredibly useful. So sometimes it just helps me to just sketch and say, okay, I've got here and here, and then this is where it would be below the x-axis. For example, if we were going to sketch this graph, then if I'm thinking, okay, where is it below 0? I know that it's that part that dips down underneath, right? And it's a smiling curve. Now, what we find is we come up with these roots at -5 and 1. These are the critical values. This is where the curve is equal to 0. Now, if it's below that, then it's going to be the range of anything that's between those two values. So the solution to our inequality, I take those critical values, what would be the roots, but I know that I want what goes between them. So it's -5 is less than x and x is less than 1. So I want that portion of the curve. If you notice, be careful to notice which way the inequality sign is going, of course, because that makes a difference as to whether I'm looking for that part below the line or if I'm looking for the two branches. If I had said instead I want greater than 0, I would be looking for the part that's on the outward. I'd still be looking for those same critical values, but I'm looking for when is the curve below 0. Oh, no, I'm looking for when is the curve above 0. So the critical values are the same, -5 and +1, but I'd be looking for when x is less than -5 or when x is greater than +1. So if you're going to solve something where you have the quadratic that is less than or greater than to 0, you can just factorize the part that's the curve. Then you get the critical values. So what would be the critical values here? This factorizes into x minus 5, x minus 2. What are my two critical values? Quick little sketch here can let you see them. It would be 2 and 5. Now, if I want to go less than that, then I know I want the region in between. And I know I'm going to be looking for the region where x is greater than or equal to 2 and it's less than or equal to 5. If I wanted greater, then it's the same critical values, but I'm looking for that split region. Okay, here's one for you to try. Try to factorize it and think in your head, what would this graph look like and where would the critical values be, and do I want less than or greater than? Okay, pause the video and you try it. All right, welcome back. Hopefully you can factorize that into these two, x plus 7, x minus 2. So if it was equal to 0, the critical values would be minus 7 and 2. So if it's less, if I want where that curve is less than 0, then I want this region. I want minus 7 is less than or equal to x is less than or equal to 2. If I wanted greater than, then I would be looking for the split region where x is less than or equal to minus 7 or x is greater than or equal to 2. You could also write these in set notation, of course. It'd be the union of these two regions. So you can solve these now without a graph. If you factorize them, find the critical values, think about it. But without sketching or imagining, it's easy to make mistakes. So just be careful that way. Here's an example where you have a frowning curve. And if I factorize it, I can see that the roots or the critical values here would be minus 5 and 1. So Sophie thinks that then the solution is x is greater than minus 5, x is less than 1. She's made a mistake. Do you have some advice on how she could fix her solution in this case? The thing is that she has to remember this is actually a frowning curve. And if she drew a picture of it, then she would realize that where it's below 0 are the branches, not that the solution then is less than minus 5 or greater than 1. So as you're factorizing, as you're finding those critical values, it's important to visualize what would this look like, what would this curve look like, and which part am I actually wanting. Another useful thing you can do is test your solutions. If you had said, okay, I think x is in between minus 5 and 1, you can test your solution with a value in between. And you would find out that it says, 5 is less than 0. And that could have also helped Sophie to realize that this is not the correct solution to this inequality. Factorizing is nice when it works out evenly. Sometimes things won't factorize, right? And we have other ways we solve quadratic equations then. You can take the completing the square method, or you can use the formula. So if you run into one that you can't factorize, you can find the roots by using one of these other two methods. Here's an example of using the formula, and you end up getting two different values. You get a positive root and a negative root in this case. Now those two roots still would be on the x-axis. They're the places where y equals 0. And so you visualize it in the same way, just your answers aren't neat integers. It would be this region, so you can, in this case, it's written out with surds, that x would be in between these two values. Here's one for you to try. Use the quadratic formula and see if you can find the two critical values, and then what would be the region where x can be then? What would be the constraints on x? Okay, pause the video until you've tried it. All right, hopefully you came up with, you may not have left it in this form. If you had put it in a decimal form, that's also fine. You have a positive root and you have a negative root. And so the way that the curve goes, it's going to be a smiling curve, and I want to know where it's above 0. So I want it outside of these roots. So either x is greater than the positive 1 or it's less than the negative 1. One more little thing to add before we finish this topic is that if you have a modulus quadratic function and then you throw an inequality into it, you can also find the solutions by sketching a graph of the curve. Is probably the easiest way if you have the graph. For example, here's our graph of 2x squared minus x minus 1. If you wanted to know where is that greater than 2, the two lines straight up and down show us, okay, these are the points where y equals 2 would intersect with this curve. So it must be, if I want where this curve is greater than 2, then I want things that are above that. So I want the region that's on this side, the left-hand side, and the right-hand side. And that would be where x is less than or equal to minus 1, or where x is greater than or equal to 1.5. You can also solve these algebraically, but it is a little bit more complex. Remember that if you have a modulus and you lift that modulus, you can have that thing in the positive form, or you can have that thing, it would have been negative and the modulus took it out of being negative. So it could be that it is equivalent to, or is related with the inequality to the y in a negative form. And if it's in the negative form, the inequality sign has to switch because it's like you've divided both sides by negative. You'll still get the same solution. Here you'll only get two solutions because of the part of the curve that it's interacting with. In some cases, you will end up with this is the same that we were just looking at. You still have those same regions. But here's an example. If you're trying to solve this algebraically, just even sketching helps you to imagine where you might be looking for solutions, or even how many solutions you might be looking for. If I'm trying to compare this curve affected by the modulus with the value 4, then I compare it to a line that goes across at 4, and I could see that where is it below that, where is it below the line y equals 4, is in two split regions, here and here, because of the modulus which flips the curve upward. You don't have to do a lot of these in the textbook, but it's good to start to imagine them and start to get familiar with them, okay? So in this particular case, how would we come up with this algebraically? We're looking for two regions that are constrained on both sides. So it's only in this portion that it's going to be less than 4. And like I was saying, you have to know that when you have a modulus, that modulus could have been a positive value, in which case we're just comparing less than 4. Or it could have been in the negative of it, which then you're comparing to less than 4. But when I want to clear that negative, it becomes like as if I have to go back to considering the unmodulus form, in the positive, and where that is greater than minus 4 if it didn't have the modulus placed on it. So you end up with these two regions that x is between 0 and 2. You can see it on the graph here, or x is between 4 and 6. Now, how do we find that if we don't have a graph? We have to go through it step by step, and you're solving both of these modulus inequalities that come up. So you have a positive version where that quadratic is less than 4. So I solve that in the same way I've been solving other ones, where I try to factorize it, and I get my two critical values here are 0 or 6. And where would that curve be less than 0? It would be where x is between 0 and 6, because it's a positive curve, it's a smiling curve. Now if I take the negative, as I said, I'm looking at what if this modulus, what if the thing inside had been negative? And if it had been negative, now to clear that negative, I need to divide both sides by -1. And if I do that, I end up having that quadratic in an unmodulus form greater than -4. Where was it greater than -4? Then I again factorize, and I get two critical values here, there where x is 2 or x is 4. Now those values, I want to know where is that curve, and those two critical values, where is that greater than 0? It would be at 2 and at 4. So x has to either be less than 2 or greater than 4 for this particular quadratic. Now I combine these two together, and I can see that, well, x can go from 0 to 2, but then it can't go bigger than 2, but then again it can go from 4 to 6, which is matching to the graph that we looked at. But when you solve them algebraically, like I said, it's a little bit more complex. You're actually creating two other quadratics, and then you're looking for the solutions to those, and then you're combining them in order to find how many values you would get for the modulus of this expression. All right, that's been a long lesson. Hopefully you can get some practice from the section related to this. What we've learned is that we can solve quadratic inequalities graphically or algebraically. We know that we can find the roots, and we need to imagine the graph when we're solving these kind of problems, and we need to pay particular attention to whether it's greater or less than to understand where the solution set is going to be found. All right, well done for giving your attention, hopefully. If you have further questions, you can ask, and this can start to feel more familiar. All right, God bless you all.